one, and then we compare them to like product 0, 1, 0, 0, 0.
How big is this vector that you're talking about?
46.
46. And what are the values in there? The probability for each category. So here would be a 0.01, and this is the probability that it's war, right? And then this would be the next probability, the next probability, the next probability, and the 42 here is, let's say, 0.9. And this is the probability that it's 42. Does that make sense? So the sum of these is 1. And if we're trying to predict a category, we get these probabilities out. How would we predict a category? Max seems reasonable. And we could even, let's say there was no probability it was greater than 0.2. What might we say? I don't know. We do not have high enough confidence to ship this to a human editor to go determine the category, right? Find a mechanical Turk to do it for us.
Doesn't y has to be the same format as y?
That is like such a good leading question. I love it. So that's just where I was going to go. Y hat and y have to be the same in order to compare, right? And so therefore, we need to convert y to actually this encoding of a bunch of zeros, and then a 1, and then a bunch of zeros, which is called what kind of encoding? 1 hot. Yep. So this is 1 hot. Encoding. In Keras, you can, and we'll see an example in here, provide y in either form, as long as you kind of tell it which way you're doing, because it is so common that you have a categorical variable that you need to compare 1 hot, and so it'll just do that comparison for you. Danny?
Would it be worse for like the learning process if you made the y hat like the max index, like what the actual prediction is, and then your error is always 0 or 1?
Yes.
Instead of like it is worse to learn?
It'd be a lot worse if, and to make sure I get your question right, so let's say you left y at 42, and y hat was a number between 1 and 42, right? So it's its prediction. But there was no idea of like how confident it was. And so it'd just be very difficult to come up with a good gradient, right, really, because it'd really just, as you say, be 0. I either got it or I didn't get it. And so it's going to be a very crude measure. So it's going to be really hard to get into high accuracies because we will want to be pushing these probabilities so that this really is really pretty certain that it's what it is. So it's for exactly the same reason on a binary classification task. We don't want the output of the neural network to be yes or no. We want it to be some probability so we can really measure how good it's getting. It's a game of what's the game called? Hot and Cold? Is that the name of the game? Warmer, 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 warmer. It's like that, as opposed to just go stumble around, and when you hit it, I'll say, burning hot. Because that's kind of what it would be like.
Yeah.
And actually, that's not a bad analogy. Reinforcement learning, I guess, is slightly different, but has a little bit to do with neural networks. In reinforcement learning, there's this idea of you get a reward for taking actions. So there's an agent that takes actions in some environment and gets some reward. And it is very much like you have to design a reward function and design what the reward is. It's a lot like training dogs. Okay, if you've ever tried to train a dog to do some trick, you need to give it some reward when it does something, like if you're trying to teach it to shake. If, one paw seems to like just a little, not even come off the ground, but they're moving a little, it's like give them reward. And then you start shaping and give more and more reward. And so it's getting feedback, really, along the way. That's kind of the analogy here. Okay, so we know what our y is, we know what our y hat is. This is one possibility, but I think we're not actually going to use this one. Yes?
So this is trying to fit our input, like our article, into one of these 46 target categories.
Exactly.
It's not saying that, okay, this could be about war, but also about finance.
That would be multi-label. Yeah, so it's possible, well, for this particular problem, there's just one. But there are certainly cases where you have multiple labels. And we will go ahead and discuss that just a little bit. By the way, one other thing is, this afternoon, I need to cancel office hours, and we're going to break 5 or 10 minutes early. So just a heads up there. We're not going to use this approach. Okay, we're going to use an approach that can accept an article of arbitrary length, which is nice, which this one will not. Whatever length you specify here is fixed. If you had a larger article, you'd be out of luck. What we'll lose, however, is the relationship, the ordering between the words. So here, we maintain our ordering. We're going to switch to, instead, bag of words, where we also have a fixed length input vector, but it's not fixed length, it is k big. K plus 1, really, because we have the unknown value here. So it's going to be k plus 1. And there's going to be a 1 or a 0. And this is if the word is present. And 0s if the word is not. So for this particular example, we'd have a 1 set for the 56th entry, the 172nd entry, the 99th entry, and the 0th entry. Does that make sense? So what we know is the article was Ezra Burke founds new unicorn. That's not really what it is. What we really know the article is unicorn, new, founds, question mark. Right? Or question mark, new, founds unicorn, or unicorn, question mark, founds new. We don't really know the ordering. But those are the words.
Why is it that we would do that? It seems like ordering could change the meaning a lot.
Yes, it could change the meaning. For the longest while, we didn't really have any way to easily deal with the meaning of arbitrary length things. We'll learn how to do that. This is what was done in the past, and this is simple and easy. So for some real model, we probably will not use this.
Is there a way to encode the frequency?
We could just change this instead of a 0 or 1 to be a number. 0, 1, or 2 or 3 that shows the number of occurrences. So we'd imagine that whatever the index there, has a large number. Yeah. Other questions? Okay, what comes out, we're going to have the neural network take a detour here. So what comes out is our y hat, right? I'm interested actually in the last layer. This is the last layer. What's this last layer look like? We got y hat coming out here. We know the form of y hat. It is a vector of 42 values between 0 and 1. So the last layer, how many outputs does it have? Everyone? 40. Did I say 46? Where did I get 42? Oh, that number is 42. Yeah, but it's 46 wide. So it's of size 46. And what does the activation layer look like? That is, what is the function? Sigmoid. Because sigmoid gives us numbers between 0 and 1. Is that right? Sigmoid gives us numbers between 0 and 1, but we have something else we need. Right? We have another requirement of these numbers. Right? What was the requirement of the numbers, Santi?
Do they have to add up 1?
They have to add 1 because it's a probability. So sigmoids won't work here, right? Because we would get independent 0 to 1s. So our last layer is going to be a softmax. We only saw this once, which is why I'm doing it again. Our softmax looks like these are our z's coming out, our 46 of them, right? So this is z1 through z46. And these are going to get e to the xth. So e to the z1, and this is e to the z46. So this value is in what range? Hello. Our e to the z1. So let's say z is negative 100. Is that in the range 0 to 1? Actually, I think it is. E to the negative 100 is 1 over e to the 100, so it's a small little number near 0, right? What about if z is 100? E to the 100 is less than 1 or greater than 1? Greater than 1 by like a lot. Yeah. So these are numbers between 0 and infinity. Yeah.
So basically each z can span like more than 0 and 1.
Each z, right, if we think of our z, right, our z is xw plus b. We don't have any limit on our w's. We don't have any limit on our b's, so they're a whole range of values. Any floating point value. Santi?
Does Grady discriminate sliding the probabilities?
Well, what it will also, well, it is certainly the case that larger numbers here, a small change in the z output is going to produce a large change in the e to the z, right, in our activation. We're not quite done though, because these are like large numbers that are, these aren't probabilities, right? They're a bunch of non-negative numbers. Which that's kind of nice, because non-negative, we know probabilities are non-negative. The only real problem here is these are not between 0 and 1. Well, not only that, they're not between 0 and 1, and they don't sum to 1. But we can fix that by scale by their total, right? So let's see how we can do this. E tot equals the summation of all these. And so, I'll put it this way. So these will all divide by E tot. So we've got ourselves numbers that are between 0 and 1 that sum to 1. And this is called softmax. Okay? Softmax, this is a hard maximum, right? The maximum is 1, the others are 0. This is sort of a softer approximation of that, a smoother version of this. Does that make sense? Question? All right. And then what do we do? So that is our output activation function, and now we need a loss function. And our loss is just going to be cross entropy. It's actually very similar to the binary cross entropy. It's just the summation over all I of y sub I, which has taken on what values? 0 or 1, times log of y hat sub I, with a minus in there so that we can do the appropriate minimization. So that if y hat sub I were 1, then that term would be 0, and all the other terms would be 0 too, and we'd have no loss. Does that make sense? All right. We are not going to look at the derivative of this one. It's a hair complicated, just because we've got this case here basically where z1 depends on or rather A1 depends on all the Z1s because of this total here. But we'll just go ahead and assume that the derivative is findable, which it is. Okay. Questions so far? We talked about normalization. And one part of normalization we talked about was noise injection. Noise injection, we talked about injecting into the input. We talked about injecting into weights, remember? So that basically, as you're doing your computation here in your neural net, make tiny adjustments to the weights so we get some noise there such that it can't fully memorize because the values are changing. We can also do another form of noise injection on the output. Okay? On the target, we can actually say, so let me adjust this here. So this is under the category of regularization. Under the subcategory of noise injection. Something that's called label smoothing. So if y is 42, which we decided was equal, I'm going to make a smaller array here. I'm going to, for a second, just assume we only had 10 categories instead of 42, so I don't have to write as much. So instead of having, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or this is the one hot encoding, right? For y equals 1, 2, 3, 4, let's say 5. Always have these questions of whether we're 0 or 1 based, and I'm just don't forget that. Smooth y would basically say, you know, we don't know for absolute certain that this is a 5, right? We had humans do this. There is a possibility that it was something else. This is maybe only 0.99 likely that it was a 5. And there's a 0.01% chance, sorry, that's 1%? Let's make it 0.1% chance that it was something else. If it was something else, what was it? Where would the rest of the 0.01 go? The picture looked good everywhere else. That's right. So we'd have 0.001 divided by 9, right? .001 divided by 9, ... Can you see how that gives us a smooth version of this, right? We're not 100% precise. So it takes advantage of the fact that there might be mislabeling, right? You can't fully trust. And the other thing that it does is our particular loss function basically says, until you get to a 1, there's a loss, right? If we have one hot encoding. Right? When this is a 1, the loss is y hat sub I. In fact, so if y hat is almost 1, we're still going to get a loss. And it's going to be basically pushing us ever and ever higher, trying to get a better loss, which is going to cause us, ignore the softmax for a moment, right? Well, don't ignore the softmax. So it's going to want this z to become bigger and bigger and bigger and bigger and bigger and bigger. That's what the loss is going to push us to. Well, by the time this is huge, do we really need to be 10 times huge? Probably not. And so by having a slightly smaller target, once we get to 0.0999, good enough. We got 0 loss. hold on, is that really how I want to think about it? 1 second. I will talk about that again on Wednesday as I think about it more. Okay. Let's look at the code here. So we have got this is TensorFloat again. So we have this Reuters data set that gets loaded. We have 9,000 training examples and about 2,000 test examples. They're all just a bunch of these word indices, just like we talked about. And there is a dictionary that allows us to go back from indexes to words and vice versa. And we can see here, for example, question mark, question mark, question mark said as a result of its December acquisition of Space Co., it expects. So, I don't know what these were. Neil deGrasse Tyson, that's right. That's a good one. Ezra, unknown middle name Burke. Could have been. And then we have the 46 labels, which are numbers between 0 and 45. We go ahead and create, so in results, we're creating this bag of words representation. And we then take our labels and convert them to one hot. So that gives us our training labels. And there is a conversion that'll basically two categorical does this one hot for us, if you'd like. So you basically just pass it an array of values, and it will then convert them into a one hot version, looking at what the particular values are, how high they go, right? So whatever the max is, and that'll be the length of each one hot. So this is more interesting now, right? So let's look at what this model looks like. Our input shape is 10,000. 10,000 represents not the number of training samples. Another guess. It's the bag of words. It's how big the bag is. It's the bag size, in fact, right? So we have the 10,000 most common words, and that's what it's using here. So our K there is 10,000. And we're going to use 64. So the first layer has how many weight coefficients? So the array, the weight array, is what dimensions? What by what? Number of inputs is 10,000. Number of outputs is 64. So therefore we have 640,000 weights there, right? And then we go from 64 to 64 again. So right, we'll have another layer. And then we'll have another layer with our 46 outputs. So this is a pretty simple model here, right? How do we choose 64? Trial and error, I guess. There's actually an example later on in this notebook where we choose 6. I think it's 6. Do you think that would perform more, better or worse than this? Or, what if I made it 1? You have to basically bottleneck everything about your learning through a single integer. Okay, how much can you express in that integer? Well, I mean, I guess if you've already learned all the categories, you could just be outputting a number between 1 and 64, right? But it becomes difficult to compress everything through this bottleneck. And so we try not to have too small of a bottleneck. So 4 is just a number that happens to work. And it doesn't overfit. Yeah.
If you have too many, does it overfit then? Like if you have like 1,000 instead of 64?
I'm sure if we did 10,000 and 10,000, that we would definitely overfit. We just have so many degrees of freedom. Yep. And this is our softmax output. Yes, so we go with 64. Categorical cross entropy. So this is the cross entropy I was just talking about. And our metric is accuracy, which is what we normally train. So we train for 20 epochs with a batch size of 512. And we press in our validation data. So we can see this is training super quick, right, at 1 second an epoch, which makes sense. We only had some number of thousand training samples. 7,982, in fact. And so that goes quickly with or without GPU. Goes pretty well. And so we're getting an accuracy of, well, let's just look at this right here. At our last epoch. Our validation accuracy was 0.80. Our training accuracy is 0.95. What do we think is going on? We're overfitting, right? So if we move back, we can kind of see where we stopped overfitting, but maybe we'll have a nice display. Oh, there's a nice display, right? So we can see, well, I don't know, 20 epochs is definitely too much. You know, maybe the number is more like here or something, maybe here, I don't know, but certainly no more than 10, okay? I'm sorry, this was the loss, and this is the accuracy. So from here, I think we would tend to say, you know, somewhere in this range is where we want to stop. Maybe 5, 4. Maybe the accuracy is going down. Maybe we can say it goes up and up and up, and then sort of down around here or something. So we'll keep going while it increases, and we'll stop afterwards. It's somewhere in this range. Okay, so this runs on 8 epochs. And then we evaluate on the test set. How many times are we going to evaluate on the test set? Just once. So as soon as I show you that number, we can never go change our model and use that test set again. So are you sure you want to see it? Let's just try it. And let's look actually and compare our validation accuracy against our final test accuracy. What's our hope?
They're about the same, or
the Yeah.
test is maybe better?
It's hard to imagine how the test could be better because we could only have been training towards the validation, right? If we're tweaking our number of layers and our size of each layer and so on. But we hope it's not too far off because we were using our validation accuracy this whole time to try and tell us what to do. And now we'll see what it really will be if we have similar data. And so 818, 919, so it's a little lower, right? 78% as opposed to the validation accuracy of 81%. So in general, assume that your actual generalization accuracy and loss is going to be certainly no better and probably a little worse than your validation. Unless you just happen to make one model and you ran it and you trained and then you looked, you would expect your validation accuracy and loss to be, you know, other than randomness, identical to your test accuracy and loss. Concept make sense? Any questions on that? All right. So 78%. Are skip that a second. We can look and we can do predictions, right? Given a particular value, it gives us this 46 by 1 by 46 vector. I'm not going to show you that. I want to show you this. So let's look what happens when we put this bottleneck in. So instead of 64 in the middle, we have 4. So represent all we know about these bag of words with 4 numbers. And I would expect we'd do worse. And in fact, we have a validation accuracy of around, we were like at 81% before, and now we peak at like 71%, right? So definitely worse. You can use these bottlenecks for good, right? For actually some value. So if you have a neural network that kind of conceptually goes down to a bottleneck, and let's say it comes back out. And let's say this is your x as input. And let's say your y is equal x. That is, I'm trying to predict my input. So if my input is 5723, then I want the output to be 5723. Well, it's certainly easy to generate labels for that data, right? All data is self-labeling. And let's say this is of size 2. Really what I'm saying is, can you compress 4 numbers into 2 numbers? This is like a compressor. And this is a decompressor. Usually this is actually called an encoder and a decoder. Can you see how that works? So we can, if we had good enough neural networks, we could maybe be feeding in images in here and looking at the images that are resulting here and have its own JPEG, that it invented in the middle. We'd expect it to be lossy, right? But it's an example of what one can do with neural networks. Any questions on the multi-class categorization? Let's change the picture to multi-label, and then we'll go on to regression. Right, so this is multi-class. Multi-label. Right, our input comes into our neural network. We have our last layer. Let's say we did a version of Reuters where we could have something that belongs, right? So if we talk about Mondays, they always have, I noticed an article that says, the leading box office was for, what's the new movie that came out? Joker, yes. So it grossed 175 million on its opening weekend. That certainly seems to be an entertainment and a finance type thing. So we're going to have multi-label, so we can be something like entertainment, check, and finance, check. So what would our Y look like in this case? So we're trying to represent that this particular thing is both finance and entertainment. Would a 1-hot encoding be good? No. How many hots would be good for this particular example? 2 hot, right? We got 2 of them that are on. So there'd be a 1 here and a 1 here, and the rest would be zeros. Could we have them all zeros? We could, right? We could have a none of the above label. We can, in a general sense, if we have multiple labels, sometimes there are things that have no labels. Or it could be all ones. If, yeah, it ticks all the boxes. It's not the Joker, it's the rookie or something, and it includes sports too. You know. So, our output here, the size is what? Assuming it's the same set of categories. 46. And our activation function, G equals sigmoid, right? Each independently, we've got, for the first one, what's the probability that it is the first category? What's the probability it's the second category? What's the probability it's the third category, and so on? They do not sum to 1, that's fine. Right? An alternate way to do this would be to have 46 binary neural networks. Right? What do we gain by having one? Danny?
You're learning some of the same things that would apply across classifying multiple.
Yeah, we're learning some of the same things. So we are sort of cross-task learning. So learning about whether something is a finance has a lot of similarities to learning whether something belongs to entertainment, and so on. So by having one model instead of 46 different models, well, one advantage is we have a lot fewer weights, right? We have 1/46 the number of weights, assuming we use the same kind of model. So that means we should generalize better, right? We're at less risk of overfitting. And practically, when you think about it, a lot of it should be the same. So there's a lot that it can share. So it's much easier for it to learn. Questions on that? So like once it learns to ignore the, it'll ignore the for every single one of the categories. And it'll just kind of filter that out. There's noise words here that we just don't care whether they're on or off.
So why would you choose to use a multi-class neural net when you could just use a multi-angle one and then say take the one with the highest probability or something like that?
Just because we're losing the information that it's only one. And that can be very useful for training it. All right. It's, oh, wait, let me back up a second. Let me think about that.
Because one is technically multi, if it's only one.
Yeah, I mean, then you... we can imagine a situation where we've got, let's say, so the true label is, let's say, a 1 here, right? And our y hat has a, I don't know, 0.6 here and a 0.5 here, right? We know we want this one to go up, right? And we want this one to go down. If we're in the multi-class case, there's no way, so moving this one up sort of necessarily is reducing the others. Whereas in the multi-label, moving this one up doesn't necessarily reduce the other ones down. It could be that our best loss is to reduce this, and that also could cause this one to reduce. So it might say the loss is better if we take this one to 0.55 and this one to 0.4 in the multi-label case. The multi-class case, we wouldn't have that situation. All right, before I talk about regression, we need to talk about limited amounts of data, because that happens a lot. That we don't have tens or hundreds or millions of training examples. We have a couple thousand or 1,000 or something like that. And so what do we do where we can't afford to set aside validation data? Okay? Because we need it for training. So here's what we do. This is called k-fold cross-validation. Right, normally, we've got our data set, our entire set of data, and we say, let's just whack off this and make this be validation. Yep. And if we've got lots here to train on, then, and I'm just going to ignore the fact we should probably also have some test data too, for now. So if this chunk is large, we're fine. But if this total amount is small, we got some problems. Okay, we've got two problems. We don't have a lot of data to train on, and this is a small sample, which means it can be very lossy, right? If we have, 500 training examples, 500 total samples, and we do, I don't know, let's say 450 and 50. That 50 may be an unusually bad sample, right? It's small enough that we can have potential errors just in our randomization. So what we want to do is try different sets of validation data. Here's the idea. Do this 450 by 50, let's say. So train on 450 and then validate on 50. Okay? Save the loss, save the accuracy. Yes?
Does the data augmentation apply here?
If we could do data augmentation, that's great, but we might have a particular set of data where we just don't know how to augment it in particular. But yeah, especially if you don't have much data, data augmentation is very useful. So we validate this on 50, and we'll just save, I don't know, let's call it loss 1 and accuracy 1. Okay. And then, once we have validated with this 50, so this is the second validation set. It's 50 big. This is the first validation set. So first we pick this 50 as a validation set, and this 450 as a training. And now we say, okay, let's take the second from the last 50. This will be our validation set. What will we use for training? How many samples? 450. We're going to go and throw this back one into the training, right? So now the next, I'll say do it again for another 450-50 split. And do this a total of 10 times. That's K. So this is 10-fold cross-validation. Yes?
Isn't this just essentially like tuning a hyperparameter? Like trying to, because if our hyperparameter, one of our hyperparameters is what is the validation set and what is the training set? And then this is just trying different amounts of them, or different types of them?
The way I think of it more is what we are doing is getting better and better approximations to our true validation loss and accuracy. Okay, because what we're going to end up with is 10 estimates of validation loss and accuracy. The average of those is going to be better than any of the others, right? We would see outliers in the others. Yes, Raji?
The second time it's on the validations of the supplies. It's been seen before in training.
Here's the key. When we train on this 450, it trains not having seen any of this 50, right? And then when we train on the next 450, we're training from scratch, right? This is from scratch. So since we're training from scratch, it's never seen this 50. It's really 10 separate models, all of which look the same, that have different weights and different losses and accuracies. Okay? And the average is better than the original, yes?
After we've taken 50, a sample of 50 as our validation sample, do we then remove that from being part of any future validation samples?
So we actually, that's a good point. So here's our 500. There's 10 there. This is our first validation. This is our second validation, our third validation, and so on. So there's no overlap. All right. Every training every sample is in exactly one of the validation samples. So it gets trained 9 times and it gets validated once.
So after you've done this and you've averaged everything, which model do you end up?
That is a great, you have 10 models. Which one do you use? Should we say the one that got well, we said we got the average because we thought that was best. Should we take the one with the lowest validation loss, the highest validation accuracy, and say that was a good model? No, that could just have been a lucky validation, right? We got the easy ones in that one. We want sort of an average model. We could take those 10 models and, in order to do prediction, run through all 10 and average the outputs. Okay, that's an ensemble approach, another form of regularization. Instead, what we do is we say, okay, we have found the good hyperparameters, right? We've found the hyperparameters, because we may have to do this whole process over and over again, trying different hyperparameters, right? Until we get the lowest average validation loss, the highest average validation accuracy. And then we say, okay, that's the accuracy we should expect. Let's go ahead and train with all the data. So we train a new model, but using the hyperparameters we've determined. And including the number of epochs. And that we get out. We don't have any validation for that. Explicitly, implicitly, we're using kind of the average of all the other models that we did. That's what we're going to come up with. And that, then we could break open our test set if we wanted. Did you have a question, Ezra? No. Okay. So we do all this. We save the average validation, loss, and accuracy. And then we retrain from scratch. With the same hyperparameters. With sort of the, let's call it the same hyperparameters. Right? This is one loop. We keep going until we're happy. And then at the end, retrain from scratch with all of our data. And the same hyperparameters. Okay. Who mentioned the idea of we can't pollute our training with the validation? Did you mention that? Yeah. So we don't want to have any leakage of validation data into our training. Let me show you. Let's see. An example of leakage. Unintended, but leakage nonetheless. So this is house price regression. And in house price regression, there are 400 training samples and 100 test samples. So 400 training samples, boy, we really don't want to set aside like a quarter of those for validation. So, preparing the data. So the first thing that's done in this notebook is it takes the training data and finds the mean and the standard deviation, right? Because we got information like square footage and walkability index and some other, values on totally different scales. And so we talked about normalizing the data, right? So what we had to do is take the training data and find its mean and standard deviation. And then adjust the training data by that. And then we adjust the test data too. Adjusting the test data makes sense, right? We have to rescale the test data into the same scale we're using for the training. And if we do any predictions in the future, we have to also rescale by those same means and standard deviations. So those would need to be saved and used. But here's the problem. When we adjusted the training data, we used all of our data. So it is adjusting by the mean and standard deviation of all the data. And now we're going to start to do k-fold validation on this validation set. But the data that we've normalized includes some information from here. Like let's say there were 2 or 3 outliers in this validation set. We've already scaled our training data by that to take into account that. So we had leakage. So if I look down here and look at the k-fold validation, so here's our k-fold validation where basically we go through k times and pull out some training data and training targets and validation data and validation targets, right? So we basically take out this exact subsetting. And then build a model, right, from scratch, new weights, fit, and evaluate. Where should we have been doing normalization? In here. Every single time, only looking at the partial training data and doing the normalization by that. So that the training data the validation data had no impact on the training data. Does that problem make sense? So that is one of the so on your assignment, you're going to be doing a regression like this. So here's my recommendation. Look at this in the book and also run it. It's on GitHub, lecture 12, set up for TensorFlow 2.0. Look at this, run it, and then think to yourself, how could I fix that leakage? In your assignment, you're going to need to be doing house regression. I'm going to just be giving you the data. I'm not going to be giving you the model and the code and everything else, but it would be reasonable to start with something like this code. But know that you're going to have to fix that leakage, okay? And the second interesting thing about the training data we're using, well, first off, it's not Boston house prices from the 1970s. So it's not house prices that are $25,000, right? It's from Ames, Iowa, more recently. Still, it's Iowa, so it's only a couple 100,000. But they have a lot more information. This data set has only numeric values, numeric information, like square footage or walkability or things like that. Our data set has things like the type of finish on the house, stucco, siding, categorical information. So you're going to have to learn to deal with with categorical inputs.